I think this is what we had last time, right? So basically what this lemma says is that if I have an AC0 circuit, then it can be approximated well by a proper polynomial, okay, of not too high a degree. So we will complete the proof of this lemma today, and we will also prove another lemma. Just state it for the sake of completeness. If P belonging to is upper polynomial of degree at most root n, then P differs from parity on at least one-tenth fraction of the. So we'll see. We'll see how the combination of these two will give us the theorem, and how why each of these two lemmas hold independently. So let's continue the proof of lemma 1. Okay. So we saw that we can assume that our AC0 circuit has only OR and NOT gates. And for NOT gates, we can consider the polynomial 1 minus p if the polynomial at its input edge is p. And for OR gate, the polynomial that we designed was the following. So suppose this is an OR gate. It has the polynomials p1 through pk at its input edges. So we define a polynomial p for the output edge as follows. So randomly pick sets S1 to St, which are subsets of elements from 1 to k. Okay. So this t basically comes from the parameter of this lemma. Basically, this lemma holds for any t. Okay, so whatever is the t that we start off with, the subsets that we pick will be equal to that t. So then Qi is defined as sigma for each subset Si, I define this polynomial Qi, which is just basically taking the sum of those respective pj's and squaring it up. And finally, this polynomial p will be equal to 1 minus the product of one minus Q i's. Okay. So what can we say? So suppose all these polynomials, so on a particular input, all these polynomials evaluated to 0. What can we say about P in that case? P will be 0, right? Because no matter what subsets we pick, if all the Pi's are 0, all these sums will also be 0. So the square of the sums will also be 0. So all the Qi's will be 0. If all the Qi's are 0, all the 1 minus Qi's are 1. So this product is equal to 1. So 1 minus 1 is 0. So it doesn't matter. So if for all I, Pi's evaluate to 0, then P also evaluates to 0. Okay. So now comes the other case. So suppose on some inputs, suppose there exists an I such that Pi is not equal to 0. In other words, Pi is equal to 1. So can P be equal to 0?
Yes.
P can still be equal to 0 actually, because it basically, since we are picking these sets randomly, it can happen that we do not. Okay. So let's say that this Pi is the only Pi that is 1. Okay. And in these random sets, in none of these random sets, we end up picking that particular Pi. So then again, by the same logic, this P will turn out to be 0, although that's not what we want. But let's bound that probability. What is the probability that such a thing will happen? So over the choice of one particular Sj, let's say, what is the probability that this Qj is equal to 0? Suppose there exists an I such that Pi is not 0. What is the probability that a particular Qj becomes 0? So I claim that, so let me make my claim. So I claim that this is less than half. So why is it so? There is one very easy argument, because you see the following. So let okay. So one way to look at this is that, so suppose, so there can be two cases. So either Sj contains the ith index or it doesn't contain the ith index. So suppose if it contains the ith index, then this quantity can sum to 0. Okay. So in other words, so this quantity cannot sum to 0 for both the cases. The first case where Sj contains the ith index, and in the second case where Sj doesn't contain the ith index. Okay. If I just consider this Sj minus this one particular index I, okay, in these two cases, it cannot be the thing that this sum becomes 1. Because since Pi is not equal to 0, at least in one of those cases, that thing will not be 0. And therefore, the probability that this is equal to 0, therefore, is at most half. So just verify this yourself. This is just a rough intuition why this is true, but convince yourselves. So if this is the case, then the probability that over all these sets S1 to St, the probability that P is equal to 0 is how much? Huh? Yeah, basically it's just the product of this, because if you note the way P is computed, P is nothing but the OR of the Qis. So even if one of the QIs is equal to 1, P will be equal to 1, because then this product will be 0 and therefore P becomes 1. So the only time when P becomes 0 is when each of these QIs are 0, and the probability of that happening is bounded by half. So the probability of this is bounded by 2 to the power minus P. So therefore, what this implies is there exists some choice of subsets S1, let's call them S1 star to ST star, such that, so there exists some choice of subsets such that on at most 2 to the power minus P fraction of inputs at this gate P will differ. So suppose now if I again look at this gate, and if I look at all the inputs to this gate, by this argument what we can say is that on at most so much fraction of the inputs, the output of this gate will differ from whatever the value that P is computing. Okay. So now I can just apply a summation bound. So how many gates do we have in the circuit? So the total number of gates is size of C. So therefore the number of inputs to C on which it differs from the value of the polynomial of the output edge of that circuit. So I'll just denote this polynomial by P star. Okay. Is how. So basically what I'm saying here is that suppose now this is our entire circuit C. Okay, it has inputs x1, x2 up to xn, and this is the output edge. So by this construction we have associated a polynomial with each edge of this circuit. Okay, and let's say that P star is the polynomial associated with the output edge. So on how many inputs will the value of this polynomial differ from the value of the value computed by the circuit? Yeah, so basically I can just take a very rough upper bound. So the total number of gates is size of C. On each gate, I mean I don't know, I don't even care how many NOT gates or how many OR gates are there. In fact, if it's a NOT gate, I am lucky because there will not be any error. But let's assume that all of them are OR gates, and on all the gates I make an error of this much amount. So the total number of inputs on which it will differ is size of C times the total number of possible inputs, which is 2 to the power n, divided by the amount of error. And that's what we want. Okay. So the last thing that needs to be checked is how much is the degree of P star. So the degree of P star, so I briefly mentioned this towards the end of last lecture. So if you look at a NOT gate, the NOT gate does not increase the degree, because if the input to a NOT gate is P, the output is just 1 minus P. The degree remains the same. At an OR gate, how much is the increase in the degree? So suppose for an OR gate, over all its input polynomials, let B be the maximum degree. Okay. So borrowing that same notation, then how much is the degree of P? How do you get n?
Okay, T, sorry.
Yeah, so if the maximum degree of these Pj's is P, then this the maximum degree of this Qi is 2B, and by that product it becomes 2TB, right? So now if you just go on level by level, I mean if you just do a simple, you can write down a simple recursive formula also, and what you get is that degree of P star will be 2T raised to the power T, because at the base level, at this level, all the degrees are 1. So then they go up to maybe 2T and then 2T whole square, 2T whole cube, and since the total depth is D, the total degree is bounded by 2T to the power T. So that completes the first lemma.
So proper polynomial part we have to.
Yeah, so why is it a proper polynomial? Why is P star a proper polynomial? So what happens at a NOT gate? If the input is a proper, so okay, so again from the base case, so all the xi's are proper polynomial, right? Suppose if I have a NOT gate, the polynomial associated with a NOT gate is 1 minus P. So if P is proper, then 1 minus P is proper. But what about for an OR gate? If all these Pj's are proper, then note that Qi is a proper polynomial, okay, because the way we define this, and if all the Qi's are proper, then this again takes value in 0 and 1, therefore 1 minus this will again take value in 0 and 1. So any other doubts? Okay, so now let's move to lemma 2. Okay, so let's look at lemma 2. So lemma 2 says that parity cannot be well approximated by a small degree proper polynomial. Okay, so here the trick is, so what we will do for lemma 2 is that we'll actually translate the problem. So instead of looking at this parity problem, we will look at another problem, okay, which is very similar to parity in the sense that it basically can be translated from parity by a very easy conversion, and we'll see that on how many inputs this other function equals the proper polynomial that we have, and from that we will basically find out the number of inputs on which parity will differ from this proper polynomial. So let me write it down. So the polynomial, the function that we will consider, so let's just denote it by parity prime. So this is a function from the domain minus 1 comma 1 to the power n. So it takes n bits from minus 1 comma 1 and it outputs a value in minus 1 comma 1, and it's defined as nothing but just a product of its input bits. So what was parity? Parity was the sum of its input bits modulo 2, and that was over 0, 1. Here I am looking at another function which is just the product of its input bits over minus 1 and 1. Okay. And we'll see that why this function works for us, and what is the relation between this function and parity. So first let's look at this second part. What is the relation between parity prime and parity? So what can I say about this parity prime of x1 through xn? If I want to write parity prime as a function of parity, how can I do that? Or in other words, what is the exact translation?
So parity will be on 0, 1 for n, and this is our minus 1 for
Huh?
parity will be on the input.
Parity is on 0, 1 to the power n. Yeah, absolutely. So firstly, I have to translate the domain of my xi's. Okay.
Here 1 behaves like our 0 and minus 1 is like
Exactly. So here 1 is behaving like 0 because 1 doesn't change whatever the product value is, but minus 1 basically switches it between plus and minus 1s. Okay.
plus x1 by 2.
Huh?
1 plus xi by 2. What that parity is 0.
1 plus xi by 2. What do you mean by xi by 2? Yeah, you can do that. I mean, there are many ways in which you can do this change, but maybe the easiest is just do x1 minus 1, x2 minus 1, and so on till xn minus 1. So what we get here is, so 1 gets mapped to 0 and minus 1 gets mapped to 1. Okay. So now when I compute the parity of this, it is basically, huh?
It should be
1 by 2.
parity prime of
1 minus xi by 2. x1 is minus 1 by 1.
parity of x1 xn is
Why?
parity prime.
Because if you
They will be
xi is minus 1, then this will be minus 2, right?
But what is minus 2?
1 minus 1.
Minus 2 is 1, right? We are working in F3. So this entire computation that we are doing is in this field F3. So this is the reason why we have chosen F3, because it is F3 which is the smallest field in which both these operations can be defined together with this translation. Had we been working in F2, then this kind of a translation would not have been possible. Yeah, so minus 2 is the same as 1. So basically now this is parity of x1 minus 1 up to xn minus 1 plus 1, right? So there exists a polynomial b prime of degree at most root n such that b prime and parity prime agree on the same number of inputs as P and parity. So what does the hypothesis of lemma 2 give us? So the hypothesis of lemma 2 gives us a proper polynomial of degree at most root n. Okay. Basically that should agree with parity on a certain number of inputs. So if I have a proper polynomial of degree at most root n, I can easily get another polynomial p prime which has the same degree and it agrees with parity prime on the same cardinality of inputs as p agrees with parity. Okay. Because if I just apply this simple conversion, you see that the degree will not increase. Okay. Because if I just look at p of x1 to xn and I define p prime of x1 to xn by just the simple substitution, there will not be any increase in degree, and because of this equality, the cardinality of points on which these two polynomials, these two think of them as functions, these two functions agree will be same as the cardinality of points on which these two functions. But there is a crucial difference. I mean, it's the cardinality on which it's the cardinality which is equal. It is not the set of points which are equal. Because for this pair of functions, I am considering 0, 1 as my domain, but here I am considering minus 1 and 1. Okay. So it's very important that we are looking at the number and not the exact set.
But the inputs can be mapped to each other.
But it can be mapped to each other because both these domains have the same cardinality. So ultimately what we want is just the number, so we can actually look at this entire thing from the perspective of these two functions, and that's what we do. So any questions so far? Okay, so let's see why this is true. So let H be the set of functions from okay, before doing that, so let S be the set of inputs on which these two concur. So E prime of set of x parts. I'm just using this arrow notation to denote the fact that this is a vector. So E prime of x parts is the same as parity prime of x bar, and let H be the set of functions f from S to the sphere. So what is the cardinality of H? How many functions do we have from S to F3?
Select any set of 3 to the power 2 to the power 8.
3 raised to
2 raised to
why 2? So any point here, okay, can go to one of these 3 points. Okay. So each point has 3 choices. So the total number of functions is just 3 to the power s, right? In fact, if you have any domain A and B, the number of functions from A to B is the cardinality of B raised to the cardinality of A. So basically what we'll show is that now we can associate a polynomial with every such function. Okay, so let f be one such function in H. We can construct a polynomial of total degree at most n that is basically the same as f. Okay, so we'll call this polynomial Pf. In fact, we can explicitly define this. So the way this polynomial f is defined is we have inputs x1 through xn. I just denote this by the vector x is equal to sum over all vectors y in S of f evaluated at that point times the product of minus xi dot yi plus 1 I going from 1 to n. So basically what I am saying is that you take any function from this set, we can always construct a polynomial, okay, which whose total degree is at most n. I mean, these are the n variables, and no monomial has a total degree more than n. Okay, so monomial is basically just a term in this entire polynomial, such that P of f will equal f for all possible inputs from this set S over S. So why is this? I mean, why does this polynomial work? So it's very simple. So suppose you pick an y which is not the same as x. Okay, if y is not the same as the given input x, then there is at least one index in which y and x will differ. So if there is one index in which y and x will differ, so let's say that index is j, what will be the value of this product? It will not be 0. It will be minus 1 because we are working over s. Okay, so one is 1 and the other is minus 1. So their product will be minus 1. So then this sum will be equal to 0, and therefore this entire product will be equal to 0. So the amount, and therefore this entire thing will be equal to 0. So the amount that that particular y contributes to this entire sum will be 0. But now let's suppose that y is exactly equal to x. Then what happens to this product? So this is 1, but 1 plus 1 is how much? It's minus 1. So I have a minus sitting before it, so that's plus 1. Then this product becomes equal to 1, and it's just f of x. Okay. So by definition, I mean, it's just a contrived way of defining this polynomial f p of f, but p of f by definition will be equal to f for all possible inputs over s. Actually, there are many ways in which you can define this. This is just one way of doing it. Okay. But what we have right now is that P of f can have total degree as large as n, right? So the goal, so our goal is to decrease that degree. So can I come up with an alternative polynomial? Let's say some polynomial Pf hat whose degree is asymptotically smaller than the degree of P of x. And the main crux of this proof is that, I mean, very non-intuitive and it's a very brilliant idea, is that you can actually do this. So let's see how we can do this. So let's pick some monomial. Okay, so actually what we will do is we will show that another polynomial Pf hat exists such that Pf hat is equal to F, okay, over S, and degree of Pf hat is at most n by 2 plus root n. Okay. So from n we have come down to n by 2 plus root n. So this is what we intend to do. So yeah, so let's pick a monomial. So basically this polynomial Pf hat will be the same as Pf for all monomials which have degree smaller than this quantity, will not do any change. But suppose we have a monomial, okay, it's product of some xi's where I comes from some set T, and what we have is that T has size more than n by 2 plus root n. So let's take a moment here. So what we are doing here is that look at this polynomial Pf. Okay, all the monomials whose total degree is less than this amount, I just leave them as it is. I don't fiddle with them. But all those monomials whose total degree is more than this amount, I do some change to them. Okay. So I just consider one particular monomial, which is product of some xi's with the plus or minus one sitting before it, and this is the change that we'll do. So this can be written as product of I going from 1 to n xi times product of I not belonging to T xi. If you are more comfortable, I can just use a different index here. Doesn't really matter. We keep this as I and use j here. Okay. So all we are doing is that, since again we are working over this field F3, and -1 times -1 is 1, and so is 1 times 1 is 1, I can just substitute this monomial, this plus or minus sitting before it, with this particular monomial. So is this clear to everybody why this substitution is correct? This is simple algebra. But what can we say about this? What is this? This particular term. Huh? It is parity prime. And what do we know about parity prime? So what we know about parity prime is that there exists a polynomial P prime of degree at most root n, which can approximate parity prime over this set. So this is, by definition, this is the set of all those points on which P prime approximates parity prime exactly. Okay, and since we are working only over this set, I can just substitute this monomial with this polynomial P prime of whatever the input x is. Okay. So that's the clever part, that's the trick which they applied. So now what is the degree of this final polynomial? What is the degree of E prime? E prime is root n. How much will be the degree of this monomial? So T had T was bounded by T was greater than n by 2 plus root n. So the complement of T is less than n minus n by 2 plus root n. Okay, so this is n by 2 minus root n. So root n cancels off. So this is less than, or this is equal to in fact, n by 2. So what essentially we did was, okay, so again this has the same plus or minus 8 in front of it. So essentially what we did was we took a monomial which had large degree and we replaced it with another polynomial having small degree. Therefore, the claim that we can construct a polynomial Pf hat such that which it agrees with f over all inputs from S and the total degree is bounded by this is true. It's constructively true. So any questions?
Sir,
Yes.
you have written down the degree of Pf bar is much less than degree.
Because asymptotically, because as n grows, okay, degree of Pf is n, but degree of Pf hat is n by 2 plus root n, okay, which is asymptotically smaller than n. So we'll see. I mean the reason. So yeah. So this was a loose statement to make because exactly what I mean by this. But in the next part we'll see that why that is important. I mean, but this is clear, right? I mean Pf hat will have degree that is less than that one. So how do we make use of this fact? So the number of monomials of degree less than or equal to n by 2 plus root n is how much? In fact, it's equal to actually. This is equal to sigma I going from 0 to n over 2 plus root n, n choose I. Okay. Because for each I, if I have a monomial which has degree I, this is the total number of possible monomials. Okay. And I am just summing this over I is equal to 0 to the maximum possible degree. So the number of polynomials of degree at most this quantity is how much? So what can be the coefficient of a monomial? So the coefficient that any monomial takes basically has three choices. It can be 1, -1 or 0. Okay. So if this is the total number of monomials. The total number of polynomials possible is 3 to the power whatever this quantity is. Okay. And okay, so I missed one thing here. So this quantity is actually less than. So suppose this were to be equal to n, then what is the value of this summation? It is 2 to the power n, right? But since this is asymptotically smaller than n, what we can do is that for any constant, actually we can bound this thing. In other words, we can say that this is less than n by 10 times 2 to the power n. this is again something that you need to verify. Therefore, the total number of possible polynomials is 3 to the power n by 10 times 2 to the power n. Okay. But now, what was the cardinality of H? So the cardinality of H was equal to 3 to the power s. Okay. And any function in H is basically being approximated by a polynomial of so much degree. The total number of possible polynomials is bounded by this. So the total number of functions in H is also has to be bounded by this. So if H is bounded by this quantity, H is bounded by 3 to the power 9 by 10 to the power times 2 to the power n, and H is equal to 3 to the power s. What can I say about S? Huh? S is also bounded by 9 by 10 times 2 to the power n. And S was the set of points on which they were same. Okay. So the set of points on which they differ is basically at least 1 over 10 times 2 to the power n, which is what we want. And although this entire thing was with respect to the parity prime function and p prime, because of our initial observation that the cardinality doesn't matter, I mean whether we are working with p prime and parity prime or p and parity, the cardinality is the same, therefore lemma 2 falls. So I'll just stop here, and why the theorem follows from these two lemmas is just plugging in the parameters. It will not take too much time. We'll discuss that on Friday.